Today we want to look at calculating the cross product. Let's remind ourselves of what the cross product is going to tell us. If we have two vectors v and w in R3, then the cross product will give us a vector that is perpendicular to both v and w, and this is useful. Notice that I have two non-collinear vectors v and w. We are defining a plane. For those of you who've been through linear algebra, that plane will be the span of the vectors v and w. But since we're in R3, taking up two dimensions with a plane is the same as excluding one dimension. So another way we can describe the plane containing the vectors v and w is to talk about the plane that's perpendicular to one vector, called the normal vector. So v cross w is a way that we can find one of those vectors. So v cross w will be perpendicular to v and perpendicular to w. So here v cross w will be perpendicular to w and also perpendicular to v. Now, this is not the only vector that is perpendicular to both v and w. There's also one going the other direction. So in the other direction, if we change the order of the cross product, if I do w cross v, then we'll have a vector going in the other direction. It is still perpendicular to v and w. So it's still perpendicular to v and w. But this makes the cross product, certainly makes the cross product an interesting thing to call a multiplication. It's another on the list of multiplications that aren't commutative. We know that matrix multiplication is not commutative. Here's another multiplication that's not commutative. V cross w is not the same as w cross v. In fact, they're opposites. The way we determine the direction is that we put our fingers in the direction of the first vector, and we curl our fingers through the shorter angle to the second vector. That's the right hand rule. So if we imagine our fingers pointing in the direction of v and then curling towards w the short way, here's one angle, looks like this is about 120 degrees, and then, or we could go all the way around for 240 degrees. We sweep through the 120 degree angle, and our thumb will point in the direction of the cross product. So if I have w cross v, I point my fingers in the direction of w and sweep my fingers through the short angle towards the second vector, and our thumb will be pointing down for w cross v. So this is just helping us determine the direction, because when we have a plane, there are two normal vectors, one going up and one going down. Oh, I guess if the plane is vertical, then one going left and one going right. Unless it's vertical the other way, then one going forward and one going backward. It's all relative, so pick your favorite. So what we're going to do, let me switch cameras. What we're going to do is we're going to point our fingers in the direction of v, and curl that in the short angle through the vector w. And then our thumb will indicate what direction it goes. So if you point your fingers in the direction of w and curl them towards v, then the vector will be going in the opposite direction. So now let's do the calculation to find v cross w. To find v cross w, we can use the determinant of a matrix. We can build a matrix and then calculate the determinant of the matrix. So V cross W is going to be the determinant of the matrix. On the first row, we put I, J, and K. On the second row, we'll put the entries in vector V. So V1, V2, V3. And in the third row, we put the entries in vector W. So W1, W2, W3. We can expand around any row or column that we like, but the most convenient thing to do, since we want a vector, we want I, J, and K to be all gathered. We want all the I's, we want all the I components, the J components, and the K components. The most convenient thing to do is expand along the first row. Don't have to do it this way. It's just the most convenient thing to do. If you're familiar with determinants, this will also be consistent with W cross V going in the opposite direction. Because if I switch two rows in my determinant, I'll change the sign of the determinant. So let's make this calculation. First, I'm going to have I'm going to expand around the first row. So the first cofactor will be I times the determinant of V2, V3, W2, W3. So this is going to be the determinant of V2, V3, W2, W3 times I. Then we go to the J, and in calculating a determinant, we always alternate signs. So if we started off positive, the next one is negative. So the negative comes from cofactor expansion. So we'll subtract the determinant of the cofactor. And then the cofactor is just going to be take out the IJK row and take out the J column. So the cofactor will be V1, V3, W1, W3. And then for the third term, the K component, we'll have the determinant of the cofactor V1, V2, W1, W2 times K. We always alternate signs. So since we start positive in the upper left, the second one will always be subtraction. That's just part of calculating determinants. It's always start with positive in the first row, first column. If I expanded down the first column, it would be plus, minus, and plus again. If I expanded around the second column, it'd be minus, plus, and then minus. If I expand around the third column, it would be back to positive, negative, positive. Since the second row since it's positive in the first row, first column, it'll be negative in the second row, first column. So if I expanded along the second row, it'd be negative, positive, negative. So we're always alternating signs. This is how to make the determinant tell us something. Wasn't chosen at random. I'm sure the first attempts at calculating something with the determinant put a plus there and saying, oh man, this isn't telling us anything. But then someone noticed in all the, someone noticed in the calculations, like, well, if I just change the sign, then that works. So now we just need to calculate the determinants of these 2 by 2 vectors. So we've got V2W3 minus V3W2. V2W3 minus V3W2 times I hats. The next entry will be V1 minus V1W3 minus V3W1. And then finally, V1W2 minus V2W1. So we don't want to write this out all the time. We just want to see the pattern. We do I, so if we think about I times the determinants, just think of the V2, V3, W2, W3. So V2, W3 minus V3, W2. If I think of I as a 1, so this is the column of, this is the first column, V1, W1, so I is like a 1. Then notice that I have V2, W3, V3, W2. So I don't have, and notice that none of the subscripts ever match in any of these products. So V2W3, V3W2. In the J is in the 2 column, in the second column, and none of the components involve a subscript of 2. So I have V1W3, V3W1. Once again, no matching in our products. No 2 and no matching. And if we think of K as being a 3, then the 1s, I'm going to make a combinations of the 1s and the 2s, and no matching. V1W2, V2W1. I usually remember the terms in this fashion because I'm going the same thing and the same order all the time. V2W3, V3W2, V1W3, V3W1, V1W2, V2W1. It's always 2, 3, 3, 2, 1, 3, 3, 1, 1, 2, 2, 1. And then I just have to remember that in the determinant calculation, the second term is the opposite of whatever you get. Sometimes you'll see the determinant calculation where this middle term, we distribute the negative. So instead of V1W3 minus V3W1, you'll see this written as a plus, and then we'll change the signs inside the parentheses. So this will be as V3W1 minus V1W3. I do not know which one will be better for you to remember. Because in both cases, you got to remember something. I always put the terms in order, 2, 3, 3, 2, 1, 3, 3, 1, 1, 2, 2, 1, and then remember that the extra thing, the second one has to be the opposite. You might want to remember them all as plus and just remember the alternate thing is that the middle one is the reverse. So 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. I'm not sure what's going to click best in your mind to help you make this calculation. The only way to find out is you got to try them both. If you haven't done this calculation and you think you already know, you don't. You've got to run the calculation a couple times. If you think you already know, that's probably going to put the other one in the one that you're thinking of in favor, so that you're a little bit biased towards that one. But you should give both of them an honest try, because who knows how things remember. It's not like some kind of determination of who's cool. It's like, oh, do you remember the minus on the outside, or do you switch the order of the subscripts? And someone's like, oh, well, I switch the order of the subscripts, so everything's positive. And then you're like, oh, weirdo. Second one's negative. Because then it becomes a fight like, is it what is it, PS5 now? Versus Xbox. Xbox doesn't know how to count, so clearly the inferior product. You know what I mean? Meanwhile, sitting outside of the whole thing, people are like, oh, PlayStation, Xbox, PlayStation, Xbox. And they're like, oh, cofactor expansion. Those are the people that are like, oh, PC. So, you know what I mean? Anytime things devolve into a choice of one versus the other, right? Coke, Pepsi. Oh, that's backwards because the red one should be Coke. Coke, Pepsi, Coke, Pepsi, Coke, Pepsi. Then there's always someone's like, oh, I don't drink soda. I only drink water. And then meanwhile, so you look at those people and say, okay, thanks for not getting the point of the fight at all, not understanding the argument at all. You know what I mean? So I don't know. If this turns into a tribal fight, if I start seeing arguments about which way to remember this is better, I am just going to cancel the class. So everybody's just getting kicked out because we're not going to have any tribes up in here. You know what I mean? And by the way, the answer is Coke, but it's got to be the Mexican Coke in the glass bottle. That's the best malted battery acid. All right, what are we talking about? Let's do one of these calculations. Let's suppose that V is, let's let V be some vector. How about 2, 1, negative 3? We don't normally write the 1, but. And W will be negative 4i. Let's go with 0j and plus 1k. So we want to calculate V cross W, and we don't want to write very much. So we don't want to set up this determinant. We don't want to write all these cofactors. We don't want to write this. We just want to make the calculation. We also don't want to memorize this formula. If I find out people are like sitting down and actually memorizing this formula, and then that's incorrect as well. You want to remember how this goes. You don't want to memorize the formula. There's a difference. You don't want to memorize formulas. You want to remember them. The way you remember them is you use them. Memorizing is where you sit down with just that thing and try to remember it. That would be like looking at a printout of some lyrics and trying to remember what they are. Memorize what they are. Remembering the lyrics is just singing the song a bunch of times until it's stuck in your head. But for reference, I'm going to have the entries in V be our V1, V2, and V3. So we're just going to remember that we're just going to make a note of this, even though we're not going to normally write this down. V1 is 2, V2 is 1, V3 is negative 3. And the entries in W are W1, W2 is 0, and W3 is 1. So I need to come up with the components for the coefficients of I, J, and K in my calculation. I is going to be V2W3 minus V3W2. I remember this because I is a 1, so I'm going to use 2, 3, 3, 2. And since I want V cross W, I'm going to start off with V. So I want 2, 3, 3, 2 because I is a 1. So that's bad grammar. I am a 1. So V2 W3 minus V3 W2. I'm solidly in the make the J1 minus so that I can remember J is a 2. So I'm going to go V1 W3 V3 W1. So I'm going to have V1 2 W3 minus V3 W1. Okay. And whatever I get from that calculation, I'm just going to make it negative. And then finally, K is a 3, so I'll have 1, 2, 2, 1. So I'll have 1, 2, 2, 1. So I'll have 2 times 0 minus 1 times negative 4. Now I just need to simplify. So it looks like we're going to get 1i and I'll have 2 minus 12 is negative 10, but I'll change the sign to make it positive 10. I'll have 0 plus 4. I promised you plenty of calculations. I didn't promise you plenty of interesting calculations. And if you're looking at this and say, man, this is going to be tedious and I'm going to make a ton of mistakes, then yep. And if you're thinking, gosh, can a machine do this? Yep. But that's not the point. Look at this great training that we have in focus and concentration. Now, we like ways to check that things have worked out. So we know that this vector should be perpendicular to both V and W. So let's check that V cross W is perpendicular to both V and W, especially because this involved me doing a lot of arithmetic and I'm just not very good at arithmetic. Let's check that this is perpendicular to V and W. So let's check that V cross W is orthogonal to V and orthogonal to W. We're going to use the dot product to do this. If the dot product of vectors is equal to 0, then the vectors are perpendicular. So I'm going to calculate V dot V cross W. So that'll be 2 times 1 plus 1 times 10 minus 3 times 4. So 2 and 10 is 12, minus 12 is 0. V cross W is perpendicular to V. And then we should check W as well. So W dot V cross W. It's going to be -4 times 1 plus 0 times 10 plus 1 times 4. We get -4, 0, and 4 is equal to 0. Checks out. So if I have two vectors, v and w, that are not collinear, we're defining a plane. So the span of the set of vectors v and w, the span of v and w is a plane. So we could say the plane containing v and w is also the plane that is perpendicular to v cross w. I'm either describing that plane with two vectors, v and w, or with one normal vector, v cross w. The direction is given in pieces. The direction is 1 in the horizontal, 1 in the x direction, 10 in the y direction, and 4 in the z direction. So we're breaking direction. Once we're talking about vectors, instead of talking about direction as a slope with one number, we're breaking direction into components: x direction, y direction, and z direction. So the plane containing the vectors v and w, the plane containing vectors v and w is the same as the plane perpendicular to v cross w. If the span of v and w is the vector space H, the subspace H of R3, then the normal vector is H perp. Any questions? So when we're describing a plane, I can think about the plane containing two vectors. So if I imagine a plane that contains the vectors v and w, the plane containing the vectors v and w, so let's suppose that that's this piece of paper that we're drawing on. So I draw the vector v and the vector w. So the paper is the plane containing v and w. So one way to describe this plane is to say, consider the plane containing the vectors v and w, using those two vectors to describe the plane. Another way to describe this plane is to say, consider the plane that is perpendicular to this normal vector that is perpendicular. So if I describe this one vector, I say, think of everything that's perpendicular to this vector. Not really a good way to put it that. The plane is everything perpendicular to this vector. And so if we take one vector in R3, everything perpendicular to it will be a plane. So it's two ways. Do we use two vectors to describe the plane, or do we use one vector to describe the plane? This is important because one of the questions that we had from calculus is, what's the slope of the line tangent to a curve at a given point? When we upgrade our function of one variable from a one-dimensional curve in R2, when we have a function of two variables, if z is equal to f of x and y, then we're talking about a two-dimensional surface in R3. So the tangent is no longer going to be a line. The tangent will be a plane. We need a way to describe that plane. I can either say that the plane is all the combinations of these two vectors, or I can say the plane is everything perpendicular to this one vector. So v cross w is normal, a normal vector. We wouldn't want to say that z is v cross w, because z is just a coordinate, it's a scalar. V cross w is a vector. Normal is just a vector that's perpendicular. So perpendicular is, things being perpendicular is important. We like perpendicular. Any questions? This only seems like it's a lot to think about because it's a lot to think about. And you have to think about all of it all the time in perfect detail. So whenever we're going through math, a lot of times we like to break things down into little pieces. But having a good knowledge of math is not just knowing a bunch of little pieces. It's about seeing how all those pieces are connected. And usually when we learn stuff, we always break it down into little pieces, but knowing the thing is about how we connect those pieces. Imagine you're learning to play a song on piano or guitar or any instrument. A lot of times we'll learn the song in parts. We'll practice the verse, then we'll practice the chorus, and we'll practice the bridge. But one of the things that we also have to practice is switching from the verse to the chorus and switching from the chorus to the bridge and back again. So we need to also practice those transitions. This is very evident when we start looking at vectors in multiple different classes. So in your physics class, when you start looking at vectors, you look at them from a point of view that will be most useful to doing the problems in physics. And then when you're in linear algebra, you just consider them as columns of numbers, and you're more concerned with how vector spaces work and less concerned with what you're going to use this for, especially when you're in an accelerated linear algebra class. Now, we're here in Calc 3, we're talking about vectors again. We've got to frame them in such a way that will be useful to us here in Calc 3. But really understanding how vectors work and what we use them for is going to involve all these perspectives. Because you've got a verse, you've got a chorus, you've got a bridge. Don't just practice each individual thing. You've got to see how they're connected. You've got to practice your transitions. This happens, I think the one that we have the most experience with is the difference between arithmetic and algebra. So sometimes people say, well, I'm great with arithmetic, but algebra was a real mess. And if algebra is a real mess, then I would argue that you're actually not as great at arithmetic as you think you are. You can probably calculate the crap out of anything that comes across your desk. Maybe you're faster than your friends with a calculator. But if you still can't do algebra, you're missing an important component of your arithmetic. You're missing the part where algebra is just arithmetic. All the things that you do in algebra are things that you already should be doing in arithmetic. And if you're good at arithmetic and not at algebra, if you're good at one and not the other, then you're less good at both because you're missing the connection between the two. Now, if you're hearing me talk about algebra just being arithmetic in a more generalized form, I would argue it's like, oh, we need some more algebra training. We need some more arithmetic training. And if we had done this properly for you when you were learning algebra, you'd know exactly what I'm talking about. You say, ah, yes, algebra was when we just generalized our arithmetic stuff and we made all those connections. But it's all the same operations. You know what I mean? Maybe you don't. It's hard to tell. I wasn't there when y'all learned algebra, so I'm not sure what your algebra traditions were. Makes things difficult, you know what I mean? It's like when you have in-jokes with your friends or you make a pop culture reference and Steve Rogers doesn't get it because he's been frozen for the last 70 years. You know what I mean? That's all we're doing in math. We're just building a common culture so that we can all make these references. Any questions, comments, or snide remarks? All right. That's going to do it for today. I just realized that the way I label the dates on this on the notes is not by date, but by the week and of the semester and the day of that week. So today is the third week and it's the fourth day because it's Thursday. So I labeled it 034. And what did we talk about today? Chapter 3, section 4. That wasn't intentional. That just happened that way. All right. So today was that was the end of chapter 13. So you need to practice some chapter 13 problems. With all these operations on vectors. You also need, while you're practicing the problems, you need to be thinking about the questions that could be coming, considering this is a calculus class. Think about slope of the tangent line. Think about area under a curve. How are these vectors going to help us? And then halfway through the semester, we're saying, oh, hey, instead of functions of just scalars, let's have functions of vectors. And you'll be like, oh, no, I'm still trying to deal with this. And then I'll be like, oh, too bad. Off we go. All right, that's going to do it for today. I'll see y'all on Monday, unless I see y'all on tomorrow for office hours. So everybody have a good weekend, and thanks for playing.